Okay, good afternoon. So, for today's lecture, we will be studying about gas turbine power plants. Okay, so gas turbines are lighter and more compact than the vapor power plants. So, the favorable power output to weight ratio of the gas turbines makes them suited for transportation applications. Okay, so gas turbine power plants are usually used sa mga aircraft, no? Propulsion, marine power plants. So, this topic will is our basis for analyzing kanang mga uh, propulsion sa imong aircraft systems. So, isa na siya, no? And also, for stationary power generation, ginagamit po yung gas turbines. Okay, so, just like the vapor power plants, just like the one we use for analyzing the internal combustion engines, we'll also employ the air standard analysis. Okay, so again, I'll repeat our assumptions for air standard analysis. So the working fluid is air. So we neglect the complexities sa imong combustion processes, no? Okay, there will be change of phase. So ato na siyang gitanggal, and for simplicity, we use air. And then this air behaves as an ideal gas. And also, ang itong process of combustion which we eliminated, we replace it with an external source, heat transfer. No? Okay, so this is the schematic diagram for a simple gas turbine. So this is classified into two. We have the open type and the closed type gas power plant. So for the open type, we do not have a heat exchanger. So we just throw the working fluid into the environment, no? And then later on, sa imong compressor, so actually these are the main components sa imong gas turbine. You have the compressor, combustion chamber, turbine, and for a closed system, you have the heat exchanger. Okay, so in order to analyze this one, by the way, the work that is supplied to the compressor is supplied by the turbine, no? So as the turbine spins, produces work, and kanang work, a portion is used to drive the compressor. So how do we analyze this one is we use the Brighton cycle. So this is the Brighton cycle, and the main processes involves compressing the air from state 1 to state 2. So the pressure and temperature of the air increases, no, as i-compress ni siya. And then from process 2 to 3, there is a heat transfer from from an external source. So mo ni siya ang gi-replace nato sa kanang combustion na process. So ang effect ani mo increase ang imong temperature and pressure, and so katong high temperature nga gas imo to siyang ipaagi sa turbine to harness the energy contained in the fluid, no? Okay. So and then pag humanaw agi sa turbine, the air is exhaust sa imong environment. Okay, so ang environment nimo acts as an heat exchanger, no? Sa imong open type nga system. So later on, mobalik ra pod to state 1 ang imong fluid, no? There will be fresh nga air mosulod sa compressor, and then uh, imo siyang applyan og will undergo a temperature change, and then i-harness nimo ang energy contained ato. So that's it. That's the air standard na Brighton cycle. Okay, so since this is an open system, the work harness sa imong turbine is just apply ka og Newton's no, apply ka og first law of thermodynamics. So you will get that work output sa imong turbine is just H3 minus H4. Now for the compressor, the same process mo buhaton, you apply the energy balance, you will get this one, H2 minus H1. For the heat added to the cycle, this is just H3 minus H2, okay, over per unit mass. And the heat ejected per unit mass, no, to the surrounding is just H4, H4 minus H1. So the thermal efficiency is just the net work over the heat Q in. Okay, or this is just H3 minus H4 minus H2 minus H1 over H3 minus H2. Now, if you are interested to get the back work ratio for the cycle, okay, this parameter is useful, no, to kung gusto naman i-compare ang isa ka engine to another engine. So, ang back work ratio is that this is just the work supplied to the compressor over work output sa imong turbine, no? So, this is just H2 minus H1 over H3 minus H4. For the same pressurized, a gas turbine compressor would require much greater work input per unit mass flow than the pump of a vapor power plant. Okay, so mas dako daw og work or power kinahanglan isupply sa imong compressor kung i-compare nimo sa pump, no, for a vapor power plant. Because the volume of the gas flowing to the compressor will be many times greater than that of the liquid passing through the pump. Okay? So, ang typical back work ratio of gas turbine ranges from 40 to 80%. In comparison, the back work ratio of vapor power plants are normally 1 or 2%. Okay? So, kung dako og back work ratio, kasabot, dako ka og supply nga work sa imong compressor. Again, there is also a cold air standard analysis. Okay, so just the same rin sa ato ang internal combustion engine wherein i-assume that the specific heat is constant. Okay, let's dive in further about the ideal air standard Brighton cycle. Okay, so this is the ideal air standard Brayton cycle. Okay, so this is the process. Compression from 1 to 2, and then constant, by the way, this is constant pressure, no? So, during the heat addition process, constant pressure ay ang nahitabo, no? Constant pressure, heat addition. So, ako tong i-correct to akong statement kaganina, no? So, constant pressure ay, so, only the temperature will change during heat addition from 2 to 3. And then, from 3 to 4, this is the turbine, no? Process sa imong turbine. Again, this is constant entropy and then heat rejection to the environment, process 4 to 1. So for an air standard analysis, you can use these equations. The pseudo reduced pressure, no, sa imong table. Okay, so these equations are just used for isentropic processes. So, ma-apply lang nimo na siya for process 1 to 2 and process 3 to 4. This one. Okay, so for cold air standard analysis, again for cold air, so for the isentropic processes, you can get these relations by assuming that the specific heat ratio is constant. Okay. So later on, we will have an example for this Brighton cycle. Now, the effect of pressure ratio on performance. Okay, so going back to this diagram. So the effect of pressure ratio, kung mo increase ang imong, by the way, this is the pressure ratio, P2 over P1, no? Kung mo taas ni siya, mahimong 2 prime, so mas mudako ang imong sample diri, mas mudako imong work. Okay? So ang effect ana sa imong thermal efficiency is mudako imong thermal efficiency. So for cold air standard analysis, atong i-replace tong mga enthalpy values by these relations. So we'll find out that the thermal efficiency is just equal to 1 minus T1 over T2. Or in terms of the pressure ratio, okay, so kung mudako ni siya ang pressure ratio nimo, sa metabo ni mugamay ni siyang value. Since negative man minus 1, ang effect ana is mutaas ang imong thermal efficiency. Okay? However, there is a limit, no? Ang imong temperature 3. Ang mabtan sa imong T3 nimo, you have a limit of 1,700 Kelvin because for sa imong blade sa imong sa imong turbines. No? So this is imposed by metallurgical considerations. So taman ra daw og 1,700 Kelvin. Okay, for figure 9.12, we have two different cycles. You have cycle A and cycle B. Now, this is cycle A. This is cycle B. We have discussed that if the pressure ratio is large, it will result to a higher thermal efficiency. So, for cycle A, so mas taas ang iyang pressure ratio. No? Makita sa graph. However, the same ang inlet temperature sa imuang duha ka system. Okay? So, cycle A would have higher thermal efficiency, but based on the figure, cycle B has greater area, no? So this translate to a greater work per unit mass flow. Okay? So mas dako na siya mag-produce ng work. So the question is, do you want the higher thermal efficiency ng engine or you want the engine that would produce mas dako nga work? So muna siya mga factors. These are the factors that you need to consider in choosing the pressure ratio. No, kung ang ganahan nimo is dako ang work output, so you use kani cycle B. But if you want to use kanang engine that has the highest thermal efficiency, so probably kani imong pilion. Okay? Let's proceed with the reversibilities. Okay, sa imo ang compressor and turbine processes. For figure A, 9.13a, this is the actual scenario that would happen sa imong gas turbine. You have an irreversible na compression, and then process 2 to 3 is not constant pressure, but there will be pressure drop. Okay, and also for process 3 to 4, it will not occur isentropically because of reversibilities. So process 4 to 1, you have also pressure drop. So for simplicity, we take process 2 to 3 and 3 and 4 to 1 as constant pressure and analyze only the irreversibilities that occur at the compressor and turbine processes. So in order to account this irreversibility, you have the isentropic turbine and compressor efficiencies. So this would compare the work done by the actual versus the isentropic case. Okay, so for turbine, so dapat mas dako ang denominator. So mas dako man ang work na maproduce sa imong isentropic, so mo na nasa sa denominator. For compressor, ang isentropic work, no, kay mo man ang gamay nga work na ma-supply nimo sa imong compressor if there is no irreversibility, so that is why mo nang nasa sa numerator. Okay, so again, we'll have an example with this one. Let's proceed with regenerative gas turbines. Okay, so the turbine exhaust temperature of a gas turbine is normally well above the ambient temperature. Okay, so there is still an opportunity to harness work for the turbine exhaust gases, no? So instead of directly venting it to the atmosphere, you allow it to pass through a regenerator. Okay, so this muna siyang naitabo. Okay? So instead na ang exhaust gas from the turbine is directly vented to the atmosphere, ipagi pa ni mo regenerator. So ang purpose ana is to preheat kani the air that is coming out of the compressor, no, para sa purpose na para mugamay na lang ang heat transfer nga needed nimo diri. Okay? Okay, so instead that the heat transfer that will be needed in the combustor is H3 minus H2, so nakatipid ka og fuel because may increase naman mo ang temperature instead of T2 into Tx. So kani na lang ang amount mo i-supply instead nga kani. Okay? So you have a term, the regenerator effectiveness. So for a counterflow nga heat exchanger, so mao ni ang imo ang distribution sa temperature. Okay, so ang hotter stream mo ni ang katong sa imong turbine exhaust. Kaning cold in mo ni ang katong gikan sa imong compressor. Okay, so pagtagbuan ni nilang duha, so may increase ang temperature sa imong air, and then ang gikan sa turbine exhaust mugamay. Okay, for this is for the actual, this is for the reversible. Now you have this term regenerator effectiveness. this is equal to Hx minus H2 over H4 minus H2. Okay? Because ideally, ang imong 2, kung 100% ang imong efficiency sa imong regenerator, H4 ta ang maabtanan na niya. But since di man 100%, Hx na lang. So kung imong divide ning Hx minus H2 over H4 minus H2, mo na imong regenerator effectiveness. So this represents the effectivity of your imong transfer ng equipment, no? Okay? So again, just solve this sample problem here in the book. We have also regenerative gas turbine with preheat and intercooling. Okay, so purpose nila is to increase the thermal efficiency. So this is the scenario for a gas turbine with reheat. Okay, so you have air from the surroundings. You compress it to state 2. Heat transfer. So money, mausap sa 3. So it will pass to the turbine. Stage 1 turbine, and then another heat transfer from the combustor, reheat combustor, and then increase ang imong temperature. So pag increase ang temperature karon, i-harness na din na sa imong stage 2 nga turbine. Okay. So when reheat and regeneration are used together, thermal efficiency can increase significantly. Reheat and regeneration. Okay, so this is the setup for a gas turbine with reheat. Okay, so at first, after the air is compressed, at state 2, it enters the combustor and the temperature is increased at constant pressure into state 3. Now the air is partially expanded at turbine stage 1 to state A. Now after the stage 1, it is again preheated. So there will be additional heat transfer for the reheat combustor. So the temperature of the air will increase from A to B. This one. So, and then finally it is expanded at the stage 2 of the turbine. Now, as we can see in this graph, for there is no reheat, so the process would be 1, 2, 3, 4 prime. So, kanisa nga portion, muna ang work na gain mo by doing reheat. But also, we need to consider nga nag-add po additional fuel diri sa imong reheat combustor. So, necessarily nga mo increase ang imong thermal efficiency. But as compared sa single stage lang na expansion, ang air nimo sa imong ang 4 prime sa imong ang 4 prime ug sa 4 is mas taas ang 4 with the reheat. So there is a potential for regeneration. So according to our reference, if reheat and regeneration are used together, the thermal efficiency can increase significantly. Okay, so kung naay regeneration, so after 4, state 4, paagi na po nimo ni sa dito sa regenerator nimo. Okay, para mo lessen ang imo ang temperature dire. or malisen ang imo ang fuel nga imong need i-supply diri sa imong combustor. Okay? Okay, compression with intercooling. So what is intercooling? So intercoolers are just heat exchangers. So instead nga single stage lang imo ang compression, imo ni karon siyang multi-stage. So after compressing it at compressor 1, so the conditions sa imong air will be at state C. This one. Okay, kani C. And then imong ipaagi og heat exchanger or intercooler to remove portion of the heat at constant pressure. Okay, so muna ang temperature karon at point D. So therefore, makompress na po siya from D to point 2. Okay, so sa PV diagram mo nang nahitabo. Okay. So, i-compress and then i-remove ang portion sa heat. And then mo na po ni siyang i-compress. So kani siya nga shaded na area, this represents ang work na nawala, no, or na save nimo, or the power input nga na save nimo from kung as compared kung imo na lang sang diretso on og compress from 1 to 2 prime. Okay, so ang purpose sa imo ang multi-stage nga compression is para dili kay ka taas og delta P, no? Para dili kayo taas ang delta P or taas kayo mo ang pressure difference sa mga compression. Another one is that ang temperature also is ma-lessen nimo, no? Instead nga ga-compress ka og high temperature diri nga gas na paubos nimo, na imo na lang siyang D. Okay? So in effect na lessen nimo ang imong work na gi-supply sa mga system, but also you need to consider also the additional nga mga components nga na-add sa imong system. Okay, so if we combine those all modifications, so morning mo ang Brighton cycle with reheat, okay, regenerative gas turbine with intercooling and reheat. Okay, so the components. So imong compress diri, multi-stage compression, you pull the fluid. Okay, so mo ni ang nahitabo again kaning 2S mo ni ang kanang isentropic and the actual compression, okay, process. Okay, and then paagi nimo sa generator. Okay, so combustor, turbine 1, and then you reheat turbine 2, and then ano yung exhaust mo magagamit nimo diri sa mga regenerator. Okay, so let's proceed with the gas turbines for aircraft propulsion. So for aircraft propulsion, basically this is just the same as the Brighton cycle. However, you have additional components. You have the diffuser and the nozzle, and in between is just the same sa imo ang components sa imong Brighton cycle. So you have the compressor, the combustor, and the turbines. So this is the turbojet engine, and these are the components. Okay, for 8 to 1, this is the diffuser. So ang purpose of diffuser is to decelerate the velocity of the incoming air. So by Bernoulli's principle, pag decelerate sa imong air, it would result to an increase in pressure. So mo na siya 8 to 1. So from 1 to 2, this is the isentropic compression sa imong compressor. Okay? And then process 2 to 3 is the heat transfer from the combustor to the gases. So you supply fuel. So mo na siya constant pressure heat addition. Process 2 to 3. And then after that one, increase ang imong temperature into T3. And so the air is passed through a turbine. So mo to harness the work. So mo sa process 3 to 4. And then after that one, the gases will exit sa imong nozzle. Okay, so ang purpose po sa imong nozzle is to increase the velocity sa imong gases, no? So pag expand niya karon sa imong atmosphere, there will be thrust nga ma-produce nimo, no? So mo na siya may mag-propel sa imong aircraft. So ang work na ma-produce sa imong turbine diri is used to drive the compressor, no? So it is used to drive the compressor and also the auxiliary ng mga components sa imong aircraft. Okay, so how do you analyze the turbojet engine? By the way, before we proceed with the analysis, there are also some aircraft that uses an afterburner. So this is the turbojet engine with afterburner. So sa purpose ani is also to increase the energy sa imong gases dere. So increase yung temperature. And after that one, so this acts as a reheat device. So produce na siya og high temperature na air or fuel. In the actual, this is air fuel mixture, no, sa combustion products nimo. So you add additional energy source to increase ang karon nimong temperature. So in effect, mas motaas ang imong thrust nga ma-generate. Okay, dere mas mataas ang imong thrust. Okay, so in order to analyze the turbojet engine, again, we'll use the air standard analysis and we assume kani nga mga compression is isentropic. Okay? And by the way, kani siya nga cycle is just the same sa Brighton cycle. So applicable ra po tong analysis na to. Okay? So we'll have an example later on. Usually, ang kaning nga problem is ang gipangita is ang imong velocity nga ma-generate diri. Okay, so let's have this example, and this is taken from example 9.4 in our reference. So you have an air that enters the compressor of an ideal air standard Brighton cycle. So the condition at state 1, this is state 1, you have air at 100 kilopascal and 300 Kelvin. Okay, with a volumetric flow rate of 5 m³ per second. The compressor pressure ratio is 10. So you have P2 over P1 equals 10. The turbine inlet temperature, this one, is 1400 Kelvin. Determine the thermal efficiency, backwork ratio, and net power developed in kilowatts. Okay, so next step we will do is to plot this one in a TS diagram. Okay, so let's draw the TS diagram. So this is the isentropic compression, point 1, state 2 is okay. State 4. Okay. So this is 100 kilopascal. Since the pressure ratio is 10, so therefore this line is 1000 kilopascal. Okay. Okay, and this one is 300. This one is 1400 Kelvin. Okay. So in order to determine the thermal efficiency, we need to get the enthalpy values at every state. Okay. Okay, so at point 1, so since this is an air standard analysis, so we'll use the properties on the table A-22. Okay, so based on the table, since you're given the temperature 300 Kelvin, the enthalpy is 300.19 kilojoule per kilogram. And the pseudo-reduced pressure at point 1 is 1.386. Now we will use this one later on in order to find the values at state 2. Okay, because this is an isentropic process. Okay, so let's proceed at state 2. For state 2, PR2 or the pseudo-reduced pressure at point 2 is just P2 over P1 times PR1. Okay, so you have 10 times 1.386. This is just 13.86. So based on the table for pseudo-reduced pressure of 13.86, H2 is 579.9 kilojoule per kilogram. Okay. Okay. So we'll proceed at state 3. For state 3, you're given the temperature of 1400. Therefore, H3 is just 1515.4. And the pseudo-reduced pressure is 450.5. Okay, for state 4, we can determine the enthalpy by getting the pseudo-reduced pressure, P4 over P3. So this is just 450.5 over P4 over P3. So this is just 100 over 1000 or 1 over 10. Therefore, PR4 is just 45.05. Okay, and H4 is 808.5 kilojoule per kilogram. Okay, so and now get the thermal efficiency is just this is just equal to the work turbine minus work compressor over the heat input. Okay, so you have H3 minus H4. This is the work turbine minus H2 minus H1 all over H3 minus H2. Okay, so you have H3 is 1515.4 minus 808.5 minus H2 579.9 minus H1 300.19 divided by minus H2. Okay, therefore the thermal efficiency is 0.457 or 45.7%. Okay. Now it is this one. For the back work ratio is just work compressor over work turbine. So you have H2 minus H1 over H3 minus H4. Right? So you have, how much is this one? 579.9 minus 300.19 over 1515.4 minus H4 at 108.5. So the back work ratio is 0.396. Okay. Now last is the work developed. Okay, the network developed is just work turbine minus compressor work. So therefore, you have H3 minus H4 minus H2 minus H1. So ang value any is ilaman. Okay. So let's calculate. Okay, so the network is 407.2 kilojoule per kilogram. Okay. Okay, but since we need to find it in kilowatt, therefore we need to multiply this one by mass flow rate. In order to find the mass flow rate, we need to employ the ideal gas model. Okay, so from the ideal gas model, this is just equal to RT PV. Okay, therefore this is just equal to pressure PV. This is the specific volume. Okay, this is actually M. This is M. Right? Okay. So volume is just R bar PBRT. I don't know. PBMRT. Okay. PBMRT. MRT over P. Okay. So, since you're given ka of volumetric flow rate, ang volumetric flow rate is just m cube per second. Okay? M cube per second. Okay? Or this is just equal to area times velocity. B. Okay. Okay, so for air, PBRT. So, PBRT. But kaning R bar is R over M, or the molar mass. So may maning 8.314 kilojoule per kilomole Kelvin times we will use kaning sa state 1 300 Kelvin over 28.97 kilogram per kilomole. Okay, over pressure na 100 kilonewton per m square. Okay, so dapat ang unit ani is m cube per kg. Cancel. Kilojoule is kilonewton meter. So mahimo ni karong m cube per kg. So tama. So this is R bar over M lagi. R bar over M. R bar is 8.314 kilojoule per kilomole Kelvin, or the universal gas constant. So mahimo ni karon nga 8.314 times 300 point 860 6096 cube per kg. Okay, so we now have the specific volume, but recall that the mass flow rate is just rho AV, where kaning rho AV is just the volume flow rate. Okay, and then kaning density nimo is just 1 over rho. So mahimo ni karon nga and that is na. So the mass flow rate is just 5 m cube per second divided by 0.86096 m cube per kilogram. Therefore, the mass flow rate is 5 divided 5.807 kilogram per second. No? Kilogram per second. No, 5.807 kilogram per second. And then, since na kay mass flow rate, multiply this one sa imuang therefore, ang network will be no, 2,481 kilowatt. Anyway, mura man ang i-multiply. So, that's it. There are plenty of examples sa book. Just go over those examples.